from floods, we constrain the river to stay always in the same place. This is not natural, because rivers in nature tend to change their course. Think about the Po River. The Po River filled all of this region, from the Apennines to the Alps. So there was a gulf that was filled by the Po River, and in order to fill the whole region, it means that the Po River had to change the course several times. Now we constrain the river in the same place. This is river training, and it originates a substantial impact. Freshwater withdrawal, land use change, including agriculture, it's a significant human impact. Agriculture, think about the nitrates, the fertilizers, but not only that. It's also, agriculture requires water, increases evaporation, and therefore there is a series of consequences with feedbacks. And that's it, but the list may be longer. There is, in my web pages, there is a link to a Wikipedia page that is dedicated to human impact, which is nice. And there is a longer list of human impacts, because here I am focusing just on water resources. But even for water resources, you may find something, you may expand this list. Okay, so these are examples of what I consider hard facts. Demographic expansion, it's an hard fact. You can document it. You can provide evidence. River diversion, same thing. There is evidence. River damming, a dam is there. River draining, infrastructures are there. And groundwater withdrawals. This is something that is not so easy to document, to prove, because there are some people, even if like in this region, we are required by law to get a permission for any withdrawal of groundwater, but actually it's very easy to build, especially today, a well, because in the past, wells were more evident. They were large and they could be seen. Now, as you know, the modern technology implies that for building a well, it's just enough to put a pipe into the soil, and it can go to very high, it can go very deep, and then you put a pump into there, and that's it, and it's not visible. And therefore, the result is that sometimes there is a widespread attitude not to get any permission, because some people also don't know about that. And they just realize they build these wells and don't take the permission. And therefore, actually, even in this region, which is, it's, the administration is very efficient. We cannot really quantify how many wells are taking water from underground. It's true that most of these wells that are not known are intended for personal use, and therefore the amount of water that is withdrawn is very limited, but they are quite widespread, and therefore it's not so easy to be able to provide evidence for groundwater withdrawal, and we are incapable of estimating the real amount of groundwater withdrawals. But still, I think it is an hard fact, because we know when we know that there is indeed some withdrawal. And then extended and substantial land use change is something that can be documented. And also climate change, in some cases, it's very evident. Like, for instance, I talk about snowmelt and the dependence of water resources on snowmelt. Sometimes it can be quite documented what is the impact of warming on water resources availability when we talk about water resources depending on snowmelt. In other cases, it's more difficult. When it depends on rainfall, as we already discussed, it's not easy to estimate what is the impact of climate change on rainfall. But these are hard facts that can be considered. Just an example, and the soft facts may be global climate change, but some people may say that global climate change is an hard fact, so it's up to your evaluation how to give, what priority to give to to these drivers, especially if you are in the middle of a discussion. And sometimes it may be better to reach compromise rather than insisting on your personal convincement, even if it's well documented. Okay, and also local land use change. Sometimes if the impact on water resources is not very evident, can be considered the soft facts. Or changes of social and environmental conditions, market changes, because also the market, through economics, can have an impact on water resources, especially on the demand of water resources. And then the status of the water distribution systems, because sometimes it's not easy to quantify the status of a system, if it needs maintenance rather than not, etc. This is nowadays a matter of discussion, because water supply systems that were built in the modern era are getting about 100 years old, and their maintenance is something that needs to be considered. Okay, so this is a suggestion to try to divide in two categories, but still we have to give priorities. So, and how can we give priorities to these two categories then? I mentioned that a possible solution which you have to evaluate case by case is to further split into categories. This is a possibility. When splitting is not possible because people don't agree on splitting, moving forward with further splitting, there is a possibility, a possible solution to give priority to a series of drivers, which is the AHP, analytic hierarchy process, which is an interesting technique. We are not focusing on that in detail. However, I would like, and I think we will have time, to focus on an example of application. And therefore, to what extent at the exam I may ask about this technique will be determined depending on the actual possibility to develop an application. Because if we can move forward with an exercise, then I will tell you what are the questions that I may ask you at the exam, and I'll tell you whether these questions will be asked already at the first exam rather than starting from the second. Because when I complete the course, what I'm teaching in the last lecture, usually I don't ask at the first exam. I hope this is clear. And I will tell you clearly what is the subject of the first exam, what are possible questions, and what this will evolve starting from the second exam. But as I said, and going back to the technical level, this process, I think it is extremely interesting. First of all, what does it mean, hierarchy? It means splitting a decision as I mentioned before, splitting a complex decision in a hierarchy of simpler decisions. And this is something that we already discussed. Dividing between hard and soft facts, it's already a kind of establishing a hierarchy in the decision. Analytic means that you call for analytic support to follow this process, which may be useful once that it's difficult for you to judge by your perception or to judge by discussion with stakeholders. When the discussion becomes difficult, it may be already the case in the splitting between hard and soft facts. If the discussion becomes difficult because people don't agree, you can call for an analytic support. Analytic support means that you establish a criteria for your decision, and then you apply the criteria, the algorithm that you have established to carry out the decision for you. I give you a very simple example. Let's think about you have to decide whether or not a dam has to be built with respect to an alternative solution. And you cannot reach agreement. The alternative solution may be reducing leakage. Because when you have a disparity, an imbalance between water resources availability and water demand, you may have alternative solution. And one solution can be I build a dam because I increase water resources availability. We already discussed about this possible solution for resolving imbalance. A second solution can be reducing leakage. And then people don't agree, because some people say, okay, but leakage, I'm not sure whether or not it allows me to solve the problem, and the dam is something that is more reassuring. Other people may say, yes, but the dam is risky and that might impact on the environment. And then a possibility is, okay, we cannot decide, let's establish a criteria. And the criteria can be the economic benefit, which means that you estimate the cost of the dam and the benefit in monetary terms that may be retrieved from the dam. And then you go to the reduction of leakage. You estimate the cost of what is a campaign for identifying leakages or substitution of the water supply system. Therefore, you estimate the costs and the economic benefit. It's quite clear that the dam is probably more costly, but gives additional benefit, like hydropower, more water, and therefore more benefit. If you reduce the leakage, probably you have less benefit, but on the other hand, it's less costly. And therefore, a criteria may be, let's take the solution that is more convenient in terms of balance between cost and benefit. And people may say, okay, that's fine. And then, at this stage, you make an analytic computation, get the two costs, and the decision is done. Usually, there is an assumption, or let's say, a methodological procedure that this is a method that is based on agreeing that the criteria should be selected before applying it. Because of course, if people knew that the dam is more convenient, then of course the other party will not agree on that criteria. So first you have to agree on the criteria, and then you apply it. You don't have to simulate application of the criteria to support your selection of the criteria. If the criteria is minimization of risk, that's fine, but you decide on it before making a simulation of the outcome from the criteria. This is something that needs to be agreed, which means that if you have information to support application of each criteria, this information should not be released in advance. And it means that this can work only if this information is actually not available, because otherwise it doesn't help in reaching a consensus. So let's go back to this analytic hierarchy process. And a possible application of the analytic hierarchy process is what is called pairwise comparison. There are links in my web pages to provide information on, pairwise comparison. What does it mean, pairwise comparison? It means that, let me make an example of application. Let's suppose that you have to design a water withdrawal from a river, and let's suppose that you have to decide what is the design flow. Because, of course, you may have done a preliminary analysis with the flow duration curve, and it may come out that you have a maximum allowed flow that is equal to, for instance, x. So max flow is x. But you may decide to get less water with respect to x. And therefore, you may have three possible solutions. I say three, but the number of solutions can be unlimited. So let's suppose that we have three possible values for QD. And these three possible values are x, y, and let's say z. In general, you will not have just three possibilities. You have a sequence of possibilities. In order to simplify the problem, let's assume that you have only three values. X is the greater one, but you may decide to get less. And so some people will discuss, and they will say, I don't like that you get X because you have a strong impact on the river, and also it may give an impact to the population, because maybe that if you take a lot of water, then you have, by having less water into the river, you know, the beauty of the landscape is affected. And if there are hydropower plants, because of course the withdrawal may support hydropower production, and a huge plant is more noisy, and maybe that doesn't give so much benefit with respect to a reduced flow. And therefore, you know, the decision may be difficult to take, and then you may say, okay, let's identify criteria for supporting this decision. But the criteria may be more than one, and therefore it's more than one, you have to give priorities to these criteria. And let's suppose that the criteria are like one, economic benefit, and then two, maybe impact to environment, quantify in some way. In some way, like noise, like let's keep it generic, okay? But of course, in a technical application, you will have to define it in some way. And then a third indicator may be a fluvial ecosystem. Or let me say, instead of impact to environment, which includes also fluvial ecosystem, let me call it impact to humans, to society. So we have these three criteria, but we have to give a priority, because it's clear that if I stick on the benefit, X will prevail. I take more water, it's likely that I have more benefit. Maybe not, but it's likely. If I stick on impact to society and fluvial ecosystem, it's clear that these are minimized if I reduce the withdrawal. And therefore I need to give priority, because you know, it's clear that we cannot give the same weight to, or we cannot give max weight to benefit, because this will favor this decision, more water taken. But we cannot give also much weight to fluvial ecosystem, because we will favor. So it's not a decision that can be taken subjectively. We need an objective way to give weight, to give priority. Give weight means to give priority, but we need an analytic procedure for supporting us in that. And therefore, a way to give priorities to these three metrics, which, and the list can be longer, can be 10, is to compare them 2 by 2 and to assess what is the importance, of, for instance, of the benefit with respect to the impact to society. And then you give a weight, like you give a score, like what is, in a scale 1-10, what is the importance of the benefit with respect to impact to society? And some people may say 1, not important at all. Some other may say 10, which means max importance of benefit with respect to impact to society. And of course, it will imply that when you make the opposite comparison, impact to society with respect to benefit, the weight, the evaluation of the score must be related. So if you say that benefit has an importance of 10 with respect to impact to society, you as an individual, if you're asked what is the importance of impact to society with respect to benefit, you need to say that it's 1. And then you compare the benefit with respect to the fluvial ecosystem, and then the impact to society with respect to the fluvial ecosystem. So you compare any, in this case, criteria 2 by 2. And therefore, and this can be done individually. So you ask your stakeholders individually to make this evaluation, or you may ask your stakeholders to make the evaluation together. These are different alternatives. How to manage a decision should be decided basing also on your audience, basing on your perception on how the discussion is going. If you take individual decision, then you have to combine them, and combination can be done by averaging. If you ask the people to group together, you favor their personal confrontation on a very simple question. So they cannot reach an agreement on a decision with 3 alternatives. You ask all of them to agree on a decision on 2 alternatives. And in this way, consensus can be reached. Otherwise, you can just say, okay, I rely on individual decision and I take the average. This could be a possibility if reaching a consensus is difficult. But let's suppose that you get a general consensus on these simple decisions. Then you may build a matrix where you have it's 3 by 3, or let me make it 4 by 4 because I need the headings. So you have x, y, z, x, oh sorry, it's not x, y, z, but 1, 2, 3. 1, 2, 3. And 1, 2, 3. Okay, so what is the importance of 1 with respect to 2? We said maybe 10. Okay, and then it means that the importance of 2 with respect to 1 is 1. And then what is the importance of 1 with respect to 3? It's, I don't know, let's say 5. Which means 3 with respect to 1 is again 5. And then I just need, okay, the importance of 3 with respect to 2, or 2 with respect to 3, which is the same. Let's suppose that it's 8, 2 with respect to 3, which means that is more important. So 3 with respect to 2 will be something like 2. And then the diagonals, which means comparison of each solution with itself. This is, I don't remember, there is a convention, but let's now just put an asterisk here. Because I tell you why I put an asterisk. Because there is a mathematical convention on what to put on the diagonal. at the end of the story, you have a matrix which reflects your comparison 2 by 2 of the different criteria, and there is a mathematical framework that from this matrix allows you to get two indications, which is first, individual weights. Weights are numbers that quantify the priority. And weights, by definition, sum up to 1, which means that a possibility can be a weight of 0.7 to benefit, and then 0.1 to impact to society, and then 0.2 to fluvial ecosystems. Okay, which means weights are numbers that quantify the priority. By definition, they sum to 1. So again, there is a mathematical framework that from this matrix allows you to get weights. And there is another indication that this matrix tells you, which is the consistency of the decision. What does it mean, consistency? It means precisely what I mentioned, that if you say that the importance of the benefit with respect to the impact of society, so the importance of 1 with respect to 2 is 10, then you expect that the importance of 2 with respect to 1 is very low. But of course, your audience may not converge on this, especially if you have a matrix that involves a long list of indicators. It's not easy to remember what you decided, and even if you remembered, there might be people who don't agree in the opposite confrontation. And therefore the matrix may become inconsistent. Like if I gave 10 with a score of 10 to 1 with respect to 2, my audience may say I still won't give a score of 10 to 2 with respect to 1, because they don't agree. They want to say maybe, no, I think that the impact to society is important, and they may want to give a 10 here, which becomes inconsistent. And this analytical process can tell you what is the consistency of the decision, which means the quality of the agreement that you reached. And then once that you have weights, you may apply the weights to each criteria. Like the dam has a benefit of a number with weight of 0.7. And then as an impact to society that you need to quantify with a number with an impact of 0.1, and an impact on the fluvial ecosystem that you need to quantify with a number with a weight of 0.2. And therefore the dam gets a score. Number multiplied by the weights. And then you go to the leakage. Reduction of leakage gets a score. Number multiplied by weight. And then you select the alternative that has a max score. Of course, you may wonder, how can I give a number to impact to society? This is something that we need to discuss. There are techniques that allows you to do that. And also we need to discuss with more details how this analytical process works, because I didn't tell you some more details, like what numbers to put in the diagonals in order to make the analytic framework working. But these are details that I'm not interested in discussing now. The concept that I would like to convey to you is that when you have to give priorities to a list of things, that can be impacts, can be, like in this case, can be whatever, and you cannot reach an agreement, even if you try to split them in categories, in subcategories, then you can use this 2 by 2 comparison, which is pairwise comparison, that is a part of the analytic hierarchy process, in order to compare the alternatives 2 by 2, which becomes much easier, and then translating this pairwise comparison into weights through an analytical process. This is extremely useful in the context of sustainable development. Of course, still it's not easy. When you go to discuss 2 by 2, still it's not easy, but it's much, much easier. And as I said, I don't want to give more details now, because I hope to be able to make an exercise. I think with an exercise it's very easy to understand how it works. It's extremely easy. But if I have to explain in theory, in words, it's more difficult, and I don't think it is really something that it's appropriate now at this stage. Let's wait. If we have some spare time left, then this is a kind of detailed study that I think it's useful for you. This is part, as a scientific discipline, it's part of decision theory. It's usually decision theory is not included in engineering. Maybe in management engineering, what is called in Italian ingegneria gestionale, maybe they have something on that, but usually it's not part of the courses in engineering. And as I said, I think this is becoming a part of the background that is needed for the engineer that is working on natural resources, on the environment, and on sustainability. Because as I said, everybody agrees on the concept, but when you have to go to solutions, the solutions to sustainability, climate change require a cost, which is not just a matter of economic cost. But even if it was a matter of economic cost, only a matter of economic cost, and economic cost, as I mentioned, means taxation, means something that is difficult to reach an agreement on. Okay? Now, let's move to the next, yeah, please.
When you multiply the weights with the score for each criterion, is that the way you then get the design flow? How do you go from the criterion to the design?
Yeah, because yeah, you're right, because I referred to 3 design flows, and then I made the example of the dam and the leakage, so it was a mistake on my part. So let's suppose that you have the 3 design flows, and you agree on these 3 criteria. And then for each of the design flow, you estimate the benefit that you get from the design flow in terms of economic benefit. And you get a number. And this is easy, relatively easy. And then this number is to be multiplied by the weight. But before making this multiplication, this is a detail that I decided not to give, you have to make sure that these 3 numbers that you get from here are varying in the same scale. So you have to rescale them in the range 0, 1. So the benefit should be varying in the range 0, 1, meaning that in the 3 solution, x, y, z, if one of them should get benefit 0, and the other one should get a benefit 1. The max benefit is scaled to 1, the mean benefit to 0. And the intermediate one is rescaled according to like linear interpolation. So basically you get a value for the benefit, for the design flow x, and you multiply it by 0.7. Then you have to assign a number to impact to society in the same range 0, 1. And this can be done. There are theories for doing that. It's called utility theory, but let's forget about it for now. So you give a number to that, you multiply it by 0.1, a number to the fluvial ecosystem, and you multiply it by 0.2. And this is for x. And then you get an overall number giving the score of x. And then you compute the score of y and the score of z. Okay, now let's go back to our step-by-step procedure. Now, once that we identify what are the most important drivers, now I said we have to identify methods for assessing the effect of each driver. So if my driver, more important, is climate change, we need a method for identifying the impact of climate change, and this method should allow me to make predictions. So how can we then build a model, a generic model, that quantifies the impact on the water resource system of the selected drivers? Because remember that so far, all we discussed so far is finalized to get drivers, give priority to drivers. Okay, and then let's focus on what is the model that allows me to quantify the impact of each driver. And this model can be either based on an inductive reasoning or deductive. The two alternatives that we already discussed. So what is the impact of climate change on rainfall? We said I can base my analysis on historical data, or I can build a model. And the same categories are used here in my discussion for models to assess the impact of all the drivers. So as I said, climate change, two options: data, inductive reasoning, or model, deductive reasoning. But also for the other drivers, like land use change. Land use change, I need a model to translate the impact of land use change into water resources availability. And then I can analyze data, inductive reasoning, even for land use change, or I can build a model, deductive reasoning. Historical data